In this video, we're going to consider once again the motion of a double oscillator being a spring that has a mass attached at each end of it. And again, as we discussed in a previous video, this, for example, could be a diatomic molecule where we have a different atom attached at each end. In video number 11, we consider the motion of this system, where if we have the spring, then we compress it and release it so that mass 1 and mass 2 are oscillating back and forth. And we determine in video 11 what the maximum velocity of M1 and M2 are. And then in that same video, we convinced ourselves that the frequency of oscillation for each of these masses should be the same. And the reasoning was, by the way the system is set up, here we can imagine that the spring, original length capital L, and then it gets compressed to a spring of small l. Then we release it, so simultaneously these blocks or these masses move apart, and they keep moving apart until the spring has its maximum extension. And this happens, of course, simultaneously. That is, mass 1 reaches its position of maximum extension at the same time that block 2 reaches its position of maximum extension. Then simultaneously they start moving toward each other, and they keep moving toward each other until the block once again is compressed down to a length of small l. So, and then block 1, that has its position of minimum extension at the same time that block 2 has its position of minimum extension, and then they start to move apart simultaneously. So in video 11, we convinced ourselves that mass 1 and mass 2 are oscillating with the same frequency. And then in video 11, we proved that that was true, and we actually derived an equation for it. And that was this: the frequency of oscillation of block 1 and block 2, both are governed by this equation. And in video 11, we derived that by realizing the spring, originally of length L and spring constant K, that when these blocks are oscillating back and forth, the center of mass of the spring never changes. And then we analyzed the system from that point of view and eventually derived this equation. Well, now, in this video, we're once again going to consider that same system, a double oscillator, but now we're going to think of it from this point of view. Here we're going to measure the distance of the ends of the oscillator from some standard reference. So this could be x1, and for block 2, distance x2. The length of this spring is capital L, and again its spring constant is K. Then imagine that we compress the spring. So now block 2 is here and block 1 is here. Block 2 are now at position x2 prime, and block 1 at position x1 prime. Now the amount of displacement here, that would be equal to x2 minus x2 prime. That's the displacement on the right end. The displacement over here on the left end, that would be x1 prime minus x1. So the total displacement for our system would be this plus this. And we have that written right here. But going back here to the top, we see that x1 plus L, the length of the spring, equals x2. And we have that written right here. Or we can say that x1 equals x2 minus L. So we're going to substitute x1 with this. So we have x1 prime minus x1. That will be minus x2 plus L. And then we have plus x2 minus x2 prime. So this and this cancel, and we have that the displacement for the spring is this equation here. Now, let's just write that up here, that spring displacement, which we'll call x, that equals x1 prime minus x2 prime plus L. Okay, so imagine that here the spring is compressed. So here on mass 2, the spring force is going to push out in this direction, and for block 1, it's going to push out in this direction. And let's call going to the right is positive, and to the left is negative. Now, what is the spring force exerted on block 2? Well, back when we first started analyzing harmonic motion with just a single spring, of course, the force that's exerted on this is the spring constant times the amount of displacement of the spring, how much it's stretched or compressed. And force, of course, that's mass times acceleration. So the mass of this block times its acceleration equals this. And what is the acceleration? Well, the displacement is x. So the time derivative of x, that would be the velocity of the block oscillating back and forth. The second derivative of it, that would be then the acceleration of the block, and it equals this. And then in video 7 we proved that this oscillates back and forth with an oscillation frequency equal to the square root of the spring constant divided by the coefficient of the displacement acceleration. So here, with our system, the spring force pushing to the right on block 2, it's going to be the spring constant K times the displacement of the system. And we're just calling that x. But this is now pushing to the right, so this would have a positive sign. The amount of spring force pushing on mass m1, it's still going to be the spring constant K times the displacement x, but it's going to the left, so that will be minus kx. So this is the force on block 2, and of course force equals mass times acceleration, so we can say that the mass of block 2 multiplied by its acceleration, and that of course will be the second derivative of x2 prime. The first derivative of this will be the velocity of block 2. The second derivative will be its acceleration. So we have m2 x2 prime equals plus kx. And likewise for block 1, the force acting on it now is minus kx, because it's pushing to the left in the negative direction. And that equals the mass of block 1 multiplied by its acceleration. And that is the second derivative of x1 prime. Now, and here's our displacement. What would be the velocity of displacement, x dot? That will equal the velocity x1 prime dot minus x2 prime dot, And the derivative of L, that's just the length of the spring. That's 0. That time derivative is 0. Now here, the second derivative, or the acceleration of displacement, that would then be, of course, these two derivatives, second derivatives, x1 prime minus x2. So here we have these equations. What say then that we multiply this by m2, both sides of the equation, m2, and over here m2. And multiply both sides of this equation by m1. So then we'll have m1, m2, and over here m1. Because now we can see the acceleration of displacement, that's the x1 prime second derivative, this minus the x2 prime second derivative, this. So let's subtract this equation from this equation. On the left side we'll have m1 times m2, and we'll have this minus this, which is that. So we have the acceleration of displacement, and that will equal then, we have this minus this, so we'll have this minus this. Let's just write it out longhand. Minus m2 kx, this minus this, minus m1 kx. So it looks like we can modify the right hand side pretty easily. We'll have here on the left side m1, m2, x dot will equal, factor out minus kx, and we'll have m1 plus m2. And we can divide both sides of the equation by this. So we now have m1 times m2 divided by this. Times the acceleration of displacement equals minus kx. So this is the equation of motion for our double oscillator. And of course it's completely analogous to the equation of motion when we have just a single mass attached, this. Now let's just look at this term for a moment. We can write it like this, say m1 divided by m1 plus m2 times m2. So clearly we're multiplying m2 by a fraction. So this number is less than m2. Or if we want, of course we can write it like this. Then we would say that this is less than m1. So that term that we're multiplying by the acceleration of displacement, this is less than either mass, m1 or m2. And when considering a double oscillation system, oftentimes then this is called the reduced mass, and it's just replaced with mu. So the reduced mass, though, that involves both blocks, m1 and m2. Now, in video 7, we showed that the frequency of oscillation here is this expression. the spring constant divided by the coefficient of the displacement acceleration. So here it's going to be the same thing. We will have omega equals the square root of k divided by mu. And this then, when we say omega, the natural frequency of oscillation, we're referring to now to both of the blocks, M1 and M2, because mu incorporates both the M1 and M2. So once again, the frequency of oscillation of blocks M1 and M2, they're the same. And now mu was this. So we have k divided by mu, or we have omega, that equals the square root k times the reciprocal of this. So we'll have M1 plus M2 divided by this product times k. But that then, we say, is the frequency of oscillation for both blocks M1 and M2. Well, again, back in video 11, we derived an equation for the frequency of oscillation that applied to both blocks M1 and M2. We got this expression. Here, using a different approach, we have this expression. Let's just take a few moments, though, and compare these two equations. This one that we just derived and the one that we derived in the last video, L over M1 R1K. So let's write these at the top of the board and briefly compare these two equations. Okay, for our double oscillator system, we said that the frequency of oscillation of block 1 and block 2 are the same, and it's this equation, M1 plus M2 divided by their product multiplied by k. And remember, k is our spring constant for the entire spring. In the last video, when we derived it, we had this expression. Now, in the last video, we had it like this, so that R1 plus M1 over 2R1, that equals L, the total length of the spring. So let's write that out. We have L equals R1 plus M1 over M2 times R, or with just very simple manipulation, we can see that L equals M1 plus M2 divided by M2 times R1. So here, that's the equation we derived with the last video, but we can substitute for L this expression. So then we'll have omega equals the square root of L, that's this, M1 plus M2 times R1 divided by M2. Then we have this, M1 R1 times K. Just substituting L, substituting this in, and this cancels. And again, we have M1 plus M2 divided by that product times the spring constant, which is what we derived in this video. So these two equations indeed give us the same expression. Okay, that's it for this video. Oh, also, just to point out to you that when we had the equation of motion for this, where we had mu equals the spring constant times the amount of displacement. If we wanted to completely analyze this, we would solve that simple second order differential equation. And in fact, we did that in video 6. And even though it's a simple enough of a differential equation to solve, there is actually quite a bit in there that applied to our system of harmonic motion, and we had quite a thorough discussion of that. And that was in video number 6. And the playlist for our videos in the Analytical Mechanics series, that is at the website digital-university.org.